Okay, so record that.
You will be a YouTube sensation if you do.
I don't know if that's a good thing or a bad thing, so I'll reserve.
I would also prefer the beach setting.
Okay. I guess you'll talk me into it. It is a little relaxing until I do that.
Awesome. Yeah.
I don't know how that's going to look on the other thing. Okay, so I think if there's no questions from the stuff we've done, 4.7, you asked a question from that. 5.1, so 5.1, we're doing composition of functions. No, we haven't done composition of functions. We've done combining functions is the word I'm trying to think of. We were combining functions with the 4 arithmetic like operations. We're going to add, subtract, multiply, divide. So we talked about those things, and I don't know how this is going to look when I switch my cam. Yeah, so I guess I can't do that. Okay. It doesn't work so well when I go to the dot cam. It just shows you a beach. So let's not do that. Okay, so I think this is where we left off last time. And if you check the YouTube account, the video of this should be up. It's been loading. I don't know what's going on with YouTube, but as soon as YouTube it fixes itself, this video of me solving this should be up. And so last time we took like a g of x function. This top part was our g of x function. We plugged in an x plus 2 everywhere that there is an x. And so we did that. And so we could solve this, and it was kind of like we could think of that thing, the x plus 2, as another function, and it's kind of like we're plugging this f of x into this g of x function. And this was what we did last time, and this is leading right into compositions of functions. And so this is the notation that we use for compositions of functions. I know my dot cam is probably not the best, but this is a G, and it's a little circle, and an F. This, it almost looks like multiplication. This is not multiplication. So like I want you to like process this. This is not multiplication. This is compositions of functions. And so this is a function being plugged into another function. It is the f of x function being plugged into my g function. And so we say this, there's a few different ways to say it. This is g of f of x, or g of f of x. And so this is the sort of thing with the previous thing. If I have like f plus g of x, I don't ever want to write it like this. So this is like the symbolic sort of interpretation here.
Sorry to interrupt. It looks a little blurry. Does anybody else have it blurry?
Yeah, it's probably going to be a little bit blurry. There's not a lot I can do. It's been really weird with its auto adjustment too. Not really sure what to do about that. I'll try to figure out how to make it a little clearer, but for now I think we're just going to have to deal with this, a little bit of blur. So g of f of x equals g of f of x, and these notes are available if you need like a more clear version. If it's hard to read, they are available on the Blackboard under the class notes. And so this is a composite function, or we call it a compositions of functions. So this on the left is kind of like the definition, or the way that we write it symbolically. If you're going to evaluate it, almost never write it like this. If you're going to evaluate it, write it like this. This will help you immensely if you write out your definitions with these things. And so I really I tried to drive home that point when we did addition, subtraction, multiplication, division. I'll try to drive home that point again. One more thing I want to mention about this. When we did add, subtract, multiply, divide, when we plugged in an x, we plugged in this x to both of these functions. You might notice this x only gets plugged in once, and it only gets plugged into one of those functions. It gets plugged into the function that's closest to it. Maybe one way to think about it. Okay. Maybe also, yeah, let me throw that back up here. So maybe also worth noting on this thing, when we do compositions of functions, and I'll say this ahead of time, we'll look at it again, but it's kind of a weird way to read this because the first thing that you see here is an f of x. And so the first thing we're going to do is plug something into f of x. And then we're going to do g. And so when we do compositions of functions, something that really messes people up is typically when we read left to right. When we read the sentence, we're reading it left to right. When we read this thing, we're actually reading compositions of functions right to left. We read them backwards from what we typically read things. And I think that really flips people around. So like maybe take mental note of that. We'll do a few more applications to where you can actually see that a little bit better probably. Okay. So find a formula for the composite function g of x that converts x tons into ounces. 1 ton equals 2,000 pounds. 1 pound equals 16 ounces. So x is in tons, and we want something that's going to end up in ounces. And so first, if we start with tons, we're going to have to convert what? Tons to pounds, and then we're going to have to convert pounds to ounces. And so if I'm thinking about g of x, the first thing I'm plugging this into is my f of x. So the first thing that I'm going to do is I'm going from tons to pounds. And so my f of x function should convert tons to pounds.
Your
And
mic
so
keeps going out.
Could you repeat that?
Your mic keeps going out. It seems
Is
like
it?
when you start to write or something, you're moving and
That's weird. It should be reading it from my computer mic.
it's working good now.
Okay. Yeah, I'm not sure. Okay, thank you.
Not going out, just getting really muffled.
Okay.
But
I
anyway,
might be, yeah, let me like maybe like direct my voice maybe more towards the computer. That might help a little bit better.
okay.
Projection, right? It's an important thing. Recording experience there. So if we want to convert from tons to pounds, the formula for that is 2,000 times the number of tons is going to give you the pounds, right? And so maybe you're thinking, do I divide or multiply by 2,000? 2,000 is the conversion ratio there, right? So here's a little thing my teacher taught me back in 5th grade is what? Big to small, multiply all. Small to big, divide the pig. And so we're going from tons to pounds. We're going from big to small. It should be an operation of multiplication if that helps. So that's my f of x. Converts what tons to pounds. My g of x is going to convert pounds to ounces. You probably already kind of guessed this form would be the what? 16x. And this might be a little silly. But if we compose one within the other, if we do g of f of x, if you look in here, we have f of x first. We know f of x is this 2,000x. So what we're really doing is g of 2,000x. And if we think about g of 2,000x, that is 16 times x. 16 times the 2,000x gives me about 32,000x. And so I think they're giving you this problem, and I think they're giving you this problem to give you some like concrete sort of like real world examples. Like we use this composition of function things, right? We compose, if we do go from what, tons to ounces, we're going from tons to pounds, and then we're taking that pounds and we're converting that pounds to ounces. But another thing, what are we doing? No, we're just finding a generalized formula. I can't talk about that. Okay. Questions about this formula, how it's getting derived? So 1 ton is going to be what, 32,000 ounces, I believe is what this is telling me. I have a formula to find ounces from tons. Okay. Let's see if I can get this a little clearer, maybe. It kind of comes and goes as it pleases with the blurriness is what I've noticed. I'm trying to figure out why exactly it's doing that, but haven't found the setting yet. The other thing is I'm using some kind of weird app to use my phone as a camera, as a webcam. And so it might be something in that app as well. Turns out when you record on Zoom, it only records the camera you have set up on that device. It doesn't record like any of the screens that you have pinned. I figured that one out. Kind of a difficult way. So this says to evaluate f of g of 2 and evaluate g of f of 2. And so if this was multiplication, those things would absolutely be the same thing, right? It doesn't matter whether we do one before the other. And so this is that property we talk about. They're trying to get at commutativity, the way that these things arrive, right? And so if we do this first one, f of g of 2, looks like f of g of 2. And so if I write out my definition, I think you'll like set yourself up to like solve this thing. Because if I write out my definition, now I'm looking inside out. I'm solving these things sort of inside out. And look right here at my g of 2. Well, that's the number 2 being plugged into my g function. So that is like 1 over x plus 8. Instead of doing x plus 8, I'm doing 2 plus 8. And I still have to take an f of it. And so what I'm doing, you could probably do this, is f of 1/10. And now I'm looking at f of 1/10. Being lazy and dropping my equal signs. If I'm looking at f of 1/10, and if I'm looking at my f function, my f of x takes an x and it cubes it. So I'm taking this 1/10 and I'm raising it to the 3rd power. There's a few different ways we can do this, but I believe this should be 1 over 1,000. That's 1 over 10 times 1 over 10 times 1 over 10. It should give you 3 zeros on the bottom. So that's my f of g of 2. If I want to do g of f of 2, I write out my definition. And so we're trying to see, is this thing commutative? So f of 2. So f of 2 is like I take 2 and I plug it into an x cube function. This is going to take the 2 and it's going to cube it. So that's plugged into my f function. I still have to bring down this g. Okay, so now we're doing 2 cubed. 2 cubed is going to give me 8. So what I'm talking about is the g function evaluated at 8. Why is it? Oh, hush. It should not do that. Okay, so g of 8. Sorry, I'm talking to Zoom there. G of 8 is going to give me 1 over x plus 8. If I do that, that is 1 over 8 plus 8. It's going to give me 1 over 16.
Half of your audio is still dropped.
Is it messing up a little bit?
Like half, literally.
It's like when you're writing, like you're changing direction or something, and it's
Okay.
muffling around that when you're writing, more or less.
Okay, I'll try to fix it as best as I can. And so you might notice Are those the same thing? 1/1000th and 1/16th is definitely not the same number, right? And so if we want to find the composite function defined by f of g of x and g of f of x, so we want to find f of g of x, and we want to find g of f of x. So I want to find a symbolic representation for these things. So my g of x is represented by 1 over x plus 8. So always start kind of like from the inside out with these guys. So the first thing you see on the inside is a g of x. You know you can write out the symbolic representation of g of x. Now that we have this, my f of x looks like x to the third. I'm going to take this thing that's inside my x, and I'm going to raise this thing to the third power. And maybe it might be worth noting, like there are some similarities, some parallels between like this thing and this thing, right? The first thing I did was I plugged it into the fraction and then I cubed it. This thing, I cubed it and then I plugged it into the fraction. And so you should have like sort of parallels that you're hopefully noticing between these two. And so we did f of g of x. If I do g of f of x, you could probably guess, but it's not going to give me the same formula, right? It got different numbers here. Probably should get different formulas if we're getting different numbers. So we do g of f of x. The first thing I see inside of here is f of x. And so for my f of x, I want to write f of x's symbolic representation. Its symbolic representation is x to the third. Now I have this. I'm doing my g function with an x to the third plugged in. So my g function looks like 1 over x plus 8. And so instead of x, I want to write x cubed into its spot. Okay. And now we want to think about the domains of these guys, the domain of this one, the domain of this guy. I guess the question here is, what is going to restrict the domain? There's two main things that we have in this class that are going to restrict your domain that I can think off of the top of my head. And I think there might be more when we get to exponentials or something, but right now there's primarily two. The first commandment in math is thou shalt not divide by 0 here. And so we want to know what's going to make x plus 8 equal to 0. And so you probably already figured this out, but x cannot be the number 8 in that one. Okay. In this one, we know what x to the third plus 8 cannot be 0. And so we want to solve this. So what makes x to the third a minus 8? We hadn't really done cube roots a whole lot, but if I think about my cube root, this is going to be when my x is a minus 2. So x cannot be a minus 2 in this one. So we're same approach, set the denominator equal to 0, solve it. That's going to be your restriction. Okay. I don't know why it's giving me that. Okay. Questions? The dog is over there snoring really loudly. Okay. So find f of g of x and g of f of x. If f of x is a x minus 1 and g of x is an x to the fourth minus 4x squared plus 1. Okay. So f of g of x.
Sorry to
Yes.
interrupt again. For some reason, it says on my screen the remaining meeting time is 3 minutes.
Yeah, I'm not sure why it's doing that. That's to be honest, it's kind of annoying. It should give us. They should have dropped the time. It's been dropped previously. We've been using it all last week. I don't know why it's coming up right now, to be honest. But if I have to restart this, we might have to restart the class. I don't know what else to tell you.
Okay, cool.
There's not a lot I can do at this point. We've already kind of started this far.
Okay.
And I apologize. That is something completely new today. I like literally taught class for hours last night, and it did not do that to me. So it's been Murphy's Law on technology for me for this transfer, to be honest. Okay. So write out your definitions. F of g of x is f of g of x. And hopefully the first thing you see inside of here is this g of x function. So we're starting inside out. Our g of x looks like x to the fourth minus 4x squared plus 1. And so we're taking x to the fourth minus 4x squared plus 1. Our f of x function looks like x minus 1. So we're taking all this stuff, x to the fourth minus 4x squared plus 1. We're taking all of that as our x, and then we're subtracting 1. So if you want, I'm going to save a little space on my paper, but you might notice this is plus 1 minus 1. If you just wanted to get rid of these, you're going to get x to the fourth minus 4x squared for this thing. If we do g of f of x, the first thing you should write out that definition. It's almost like you just drop the signs and throw more parentheses in there. But this is g of f of x.
Sorry, we don't go any further on the previous answer.
No, that's fine. That's the symbolic representation right there.
Okay.
X to the fourth minus 4x squared.
Okay, so no factoring, obviously.
No, just as long as that's distributed form, that's fine.
Okay, cool, thanks.
Yeah. So g of f of x, I'm hoping the first thing you see in here is my f of x function. And that's going to look like x minus 1. And so we're doing g of x minus 1. So now we're taking our g function, we're plugging it in at x minus 1. Everywhere that there's an x. So we have an x to the fourth. And so that's going to look now like an x minus 1 to the fourth. That's going to look like a minus 4. And now we have an x minus 1 squared. And we have a plus 1. If I'm being honest, there's a little bit of cleaning up that you can do with this. Start recording this again. I have my f of x is 1 over 2x. I have my g of x is x to the fourth minus 1. And so I want to do f of g of x, and I'm going to do g of f of x.
Sorry, the previous one you said you could clean it up a little bit, but then.
Yeah, I don't want to do it. It's too much work.
Okay, cool.
If y'all show me this, to be honest, I think they kicked out all the things that look this hard. I think this might be harder than what you're actually going to look at anything. But, I mean, it's still the same concept. We're plugging one guy into the other. So f of g of x is f of g of x. And if you write out your definition and you look inside out, I think you might start to get these things. The first thing I see is g of x. I can write out that guy's symbolic interpretation as x to the fourth minus 1. That takes care of that g of x that I have in there. And I still need to plug that into my f function. So my f function looks like 1 over 2 times whatever the heck that thing is. It's 1 over 2x. And so my x here is no longer x, it is x to the fourth minus 1. I guess you could distribute this 2 if you really wanted to. If I'm being honest, and we're doing compositions of functions, as long as you show me that you know how to plug one function into the other and you get to like this step, I would be pretty happy and content in knowing that you know how to compose a function in a function. Okay.
So for the test, we should just stop there then.
Yeah, that would be fine. Because I mean, sometimes you don't always want to distribute these things either, right? Sometimes having them factored is beneficial.
Okay, yeah, okay, thank you.
And so g of f of x is g of f of x and if you look inside out, the first thing I see in here is an f of x. So an f of x function looks like did I do that? Yeah, 1 over 2x. Sorry. I was trying to make sure I did the previous one correctly. I was like, okay. So 1 over 2x. And so I plug in my f function. Now I want to plug in my f function into my g function. G function looks like x to the fourth minus 1. But instead of x, now the thing I'm plugging in is the 1 over 2x. Yeah, that should be fine there. Questions about these? Okay, so this is doing them graphically. F of g of a minus 2. And so let me go ahead and write out the definition down here. F of g of a minus 2. And I kind of talked about this, but when we do compositions of functions, we're only using this x value once. And so here's a little overview of the process. We're going to take this minus 2. My g is going to give me a y value that I get. And then I use this y value, and I use g's y value to give me an x value for my f. And then we're going to find a y value for the f and find what that is. And so it's a little weird because we go from x to y, and then from y to x, and then from x to y. But if we do this right, I think we can do this. G of a minus 2 is the first thing I see in here. And so if I want to do g of a minus 2, I'm coming over here minus 2. My g is the blue function. And if I want, g of a minus 2 should give me a value of 4 right here. So this is the minus 2. It's going to give me a value of 4. And so this thing I can write as 4. G of a minus 2 evaluates the 4. So if I evaluate my g, I still have to plug this thing into my f. And so now I'm doing f of 4. And so if I look at f of 4, this was a y value. Now it becomes this guy's x value. So now I'm plugging in 4 to my f. I come along here with the 4. And my f is going to give me the value of 2 at 4. So we do the -2, we plug it into the G, it gives us 4. We do the 4 into our F, it's going to give us 2. G of F of 1 is G of F of 1. And I'm telling you, there's always that question. Oh, hold on. Luis is waiting. Okay. And so there's always this sort of question of like, how much work do I need to show? Because people just want to like do these without showing any work. I would not suggest doing that. In my kind of smart ass responses to how much work do I need to show is always like, well, how much credit do you want to receive? Because if you give a wrong solution and you don't show any work, it's all wrong. But if you give a wrong solution and you show some work and some of that work was correct, you're gonna get partial credit. So show as much work as you want to get credit for, I guess is my answer to that one. Okay. So, who's that? So, G of F of 1. If I look at this and I write out the definition, the first thing I see inside here is F of 1. So the 1 in here represents an X value. So I come along here to my 1X value. I look at my F. F of 1 is going to give me 1. And so this takes care of my F. I still need to plug this thing into my G. And so now if I look at G of 1, now this is my X. I look at G of 1. Oh, that's 1. So this is probably not the most interesting example, but it could do that sometimes. So we have been composing F into G. We've been composing G into F. The one thing we haven't done that you can do is you can compose a function into itself. So the next thing we have is F of 0. And if you write out your definitions, I think you'll get a lot of credit for these at least. So F of 0. And so if I look at F of 0 is the first thing I see inside of here. If I evaluate F at 0, it's going to give me 0. It's going through 0, 0, it's going to give me 0. So this may not be the most interesting example. But if I do F of 0, it gives me 0. And now if we look at this, I'm gonna have another F of 0. This is also going to give me 0. Okay. Any questions about these three? I'm telling you, write out those definitions. If you write out the definitions, I think you'll get at least a good amount of credit on this.
For the previous problem, just for fun, could you do F of 4? I think that one would work out, right?
F of 4.
Well, no, I guess it's 2 would.
If we do F of 4 is going to give us the number 2. And then if we do F of 2, oh Jesus, I don't know what that's gonna be. It's not an even number, right? It's like 1.5, somewhere in there. I don't know. Just guesstimating.
Yeah, all right. But
Just
thank you, though.
guesstimating, right?
Thank you.
Yeah. Yeah, I mean, I can't give you an exact answer on that one because it's not exactly on the line. But I mean, as long as you get the concept there, right? I think the concept still comes across a little bit.
Yeah, thanks, man.
That we're going from X to Y, and then we're using that Y as an X to go from X to Y again. It's kind of a weird thing, but. Okay. Now we did things symbolically, we did things graphically. Now they're going to give us the third way numerically, right? We did things verbally too, right? We did things with the word problem, I think, to begin with. Example 10, g of f of 4. If you write out your definitions, I think that will really help you. G of f of 4. And so previously when we had a number, we would use that x twice. Here you might notice you're only using this once. And so go to the right table. Well, I think you can only go to one table. And we evaluate f at the 4 value. It's going to give us 16. And so we still need to evaluate 16 at the g value, which is going to give us 64. Okay. Okay, so now they say complete this table. We want g of f of x. So if we think about g of f of x, the first thing I'm plugging my x into is going to be which function? If we see it here, the first function is going to be my f function. And so I want x values that I can plug into my f function. So there might be a question of, do I use 2, 4, 6, 8, or do I use like 8, 16, 24, 32? Well, you want to be able to plug it into f. So use these values, 2, 4, 6, and 8. And let's do this. If I plug in 4, let's do 4. If I plug in 4, it's going to spit me out 64. That's the one we did right up there. If I plug in 4 to my f and then I plug it into g, it's going to give me 64. So how did I do this? I went from 4 to 16, and I went from 16 to 64. And so 464 should be one of the numbers in this table. Same thing, if I plug in 2, it's going to go to 8, and that 8's going to go to 32. So I don't know if you notice this, but there's this kind of middle guy right in here that we're actually like, we're using him, but then we're kind of throwing him away, right? So we go from 6 to 24, then from 24 to 96. We go from 8 to 32, and then from 32 to 128. And I didn't read it, but these actually have meaning. So F converts gallons to quarts. G converts quarts to cups. So if I go from G to F of X, I'm plugging it in. So the first thing I'm doing is converting gallons to quarts, and then I'm converting quarts to cups. And so if I put those two things together, G of X, it inputs gallons, and then it takes it to where does it go? Cups, right? And maybe labeling this might help you see that. We're going from gallons to quarts, and then we're going from quarts to cups. And so in the overall thing, we're going from gallons to cups, and I talked about the middleman that we kind of toss out. Well, that was the quarts, right? We're not even talking about quarts in this end thing, but it was important to get these two things composed together, right? Okay. So example 11, the last one here. They want us to find an f of x and a g of x such that h of x is the composition of those two functions. So we have a sort of like inside function, which is going to be our f of x. Then we have like a sort of outside sort of function. So I'm hoping you can see this. This looks like 2x minus 1 squared. And so if we look at this, I'm hoping you see two different things in here. Like there's a thing on the inside, the 2x minus 1. We can think about 2x minus 1 by itself. That's a linear function. Or we could look at that square as being a thing. And so if you think about the thing on the inside is going to be the 2x minus 1. And then what did we do to that 2x minus 1? We took it and we squared it. So they've been doing things like kind of forward. We've been taking two functions. We've been constructing it into a third new one. Now they're going kind of backwards and making you try to think kind of critically about this sort of thing. How does this look like one function plugged into another? And so the easiest way to kind of think about it to me is like there's an inside function and there's an outside function. Okay, so if we look at like two different functions here, I'm hoping you notice one of them looks like x plus 1. One of them looks like a square root of something. And so the f of x would be the thing on the inside, would be the x plus 1. And then the g of x would say, hey, we need to take the square root of that thing. And how do you say, hey, take the square root of that thing? You say, take the square root of our variable. Same thing, last one, f of x, g of x. And so I'm hoping you notice there's this thing that looks like 2 minus x. And so that's going to be our inside. We want to say, hey, put that thing over 1. And so how do you say that mathematically? We say, hey, put that thing over 1. We say 1 over x. Questions about this section? I think that will do it. So this is about combining functions. We added, subtract, multiplied, and divided functions. And then today we did the composition of functions. We finished that up. And so the last thing before the test, we might have to use Thursday to finish up a little bit on this one. But we should get through most of it. I'm hoping. I hate this. I really want to reverse the order of this because it makes more sense. And it's kind of a silly example, and I should have caught it before I put it out. But if we put on socks and shoes, I want to think about inversing operations. So if I lock the door, right? The inverse of locking the door would be like unlocking the door. If I put on my socks and then I put on my shoes, if I want to undo that thing, well, I have to take off. And if you take off your socks before your shoes, congratulations on the magic trick, I guess. But typically you take off your shoes first and then your socks. And so when we undo things, we kind of undo them in a reverse order of what we originally did them, right? And this might seem really silly to talk about taking off your shoes and socks or putting them on, right, in a math class. But there's a reason why we're talking about this, because a lot of these like concepts that we talk about in math, yeah, sure, they pertain to numbers and the numerical and everything, but they also apply to real life, right? Whether we talk about something, what is this? The commutative property. If we do socks before shoes or shoes before socks, does it matter what order we do these things in? If you put on your shoes before your socks, you're going to have your shoes wrapped around your socks, right? You're going to look a little silly. So it absolutely matters what order we do things in. So that is commutativity. We talk about commutativity all the time in the real world. We talk about it in the real world. We also talk about it in algebra. I don't know what else to tell you. But it's a concept that we use not just in algebra. It's also used elsewhere, right? What else? Associativity is the other thing. We hadn't done anything like that recently, I guess. So 5.2 is about inverse functions and their representations. So we're going to talk about inversing things formally. We've already kind of talked about this. If I want to like multiply, the opposite of multiplying is dividing. If I want to add something, the opposite of adding would be to subtract it. And so if I want to add 1 and then multiply by 4, if I want to undo that, I should go, and I've kind of hinted at it, reverse order, right? So if I want to undo multiplication, the first thing I should do is divide. And I divide by the same number I multiplied by. I divide by 4. So I divide by 4, then I'm going to undo and add 1. I'm going to subtract 1. Okay, so a little review of like what a function is and what a function isn't. So if I have something like the point an x 263 and 259, right? This was the thing that broke a function. It was when we had a repeated x and it gave us different results when we plugged it in. And so it's a repeated x with different y's, right? And so now we want to talk about inverse. And so the original function starts with an x and it will spit out a y. And inverse, you're starting with this and it's going to spit out this. And so now if we want to see if this function has an inverse function, I'm not looking for a repeated x now, I'm looking for the repetition in my y value. So if I see repetition in my y value, is that inverse a function?
No.
No. Okay, so we're still there. Making sure. Okay, so that does not have an inverse function. And it doesn't have an inverse function because of those two things I just circled. We have a repeating y value and it's giving you a different x value. Now we're looking at this one. This thing is definitely a function. None of our x values are repeating. Now we look at the y values. None of the y values repeat. So does this have an inverse function? Yes, the inverse function exists, right? I messed up with my t-cross. Still messing up. Okay, so let's think about what this means. So if you have a function, none of your x values are repeating. If you have an inverse function, none of your y values are repeating with different x values. And so there's this thing that sort of happens that like for each x, we're going to get a y. And for each y, we're going to get an x that's also unique. So for each x, we're getting a unique y value. For each y, we're getting a unique x value. And so there's this thing that happens that there's a unique value that goes with each one, right? And so a one-to-one function, what do they say in the notes? For elements C and D in the domain of F, C not equal to D implies F of C is not equal to F of D. That's a horrible way to define it, but that's mathematically how they define it in the book. I don't want to write that. But here's a way, different inputs. will always result with different outputs.
Did you also say that all the numbers have to be different?
Yeah, the way that I would really take this is if f is a function f is 1-to-1, if its inverse is also a function, is another way you can kind of look at this. Why is meeting will end in 10 minutes? Okay. And that's pretty much the way that's what they're trying to hint at. And I think I'm probably just throwing it out there and probably should have made you work a little bit more for that definition. But that is the gist of it. If you have a function and its inverse is also a function, it creates this unique pairing between your x quantities and your y quantities. So none of your x's are repeating, none of your y's are repeating, but each one of them gets paired up uniquely, right? It is kind of the gist of it. There's a unique sort of pairing that happens. Each 1x gets 1y and each 1y gets 1x, right? And that's why it's sort of called, well, that's exactly why it's called 1-to-1, right? So I'm hoping like that naming of it makes a little sense. So, function on graphs. If we want to do a function on a graph, what is that test that we use to do it?
Vertical line?
Vertical line test. Does this pass the vertical line test? Is this a function? Absolutely. Is its inverse a function? So if we think about this being a function, if we want to know whether the inverse is a function, we hadn't really talked about it, but it's like way down there on the bottom of the notes. It says it right there. You're not using a vertical line test. You're going to use a horizontal line test. So if I used a horizontal line test, would this pass the horizontal line test? Absolutely not. And why is that? I hope you can see it. Because if I draw a line through here, it's hitting it, what, 3 different spots? It's not passing that test. So if it's a function, but its inverse is not a function, is this thing 1-to-1? No. I probably should have wrote these in a better order. Probably should have said function, inverse function, 1-to-1, but note to future self. Okay, so this one does not have an inverse function. It's not 1-to-1.
Okay, so hang on. For the A we just did, it's not 1-to-1 because the y value is in the part where it fails the horizontal line test.
Yeah, so for it to be 1-to-1, it has to pass both the vertical and the horizontal, right? This has to be yes, and this has to be yes for this to be yes.
Thanks, man.
Yep. So now we're looking at this guy. This guy is a linear function, so God, I hope you're saying yes with that one. If we do this, it's never going to hit 2 spots. If we do this, is it ever going to hit 2 spots? No, it's not. So that makes our inverse a function. And guess what? Linear functions, they're 1-to-1. For each x value, there is a unique y value that you can give me, and vice versa, right? For each y value, there is a unique x value. We compare one x value to one y value and only 1-to-1, right? We're not doing multiples. Okay. All right. Symbolically, if we want to check if something is an inverse function. So symbolically, if we do an inverse and we do it, so this is like, I don't know, take a number, right? 5. If I add 3 to 5 and then I subtract 3, what am I going to end up with? I'm going to end up with the thing I started with. So if I take x and I do something to it and then I inverse it, I'm going to end up with my x. And so this is sort of the definition that I hope like you're getting at and hope that makes a little sense. But if we take something, we do a function to it, and then we do its inverse. These two things undo each other, right? And so we end up with the thing that we originally plugged in. And so if we want to check if something is an inverse, we have to use this definition right here. We plug one into the other and we see if it spits back out the original thing. So let f be a one-to-one function given by the cube root of x minus 2. Find a formula for f inverse. So we hadn't really talked about how to find the formula. This should say f of x, sorry. There should be an f of x there. But there's two main steps to finding the inverse formula. So there's going to be a swap and a solve, or you can solve and swap. It doesn't really matter what order you do them in, but you have to do both of them. I think people prefer the swap and then the solve. So if this is y equals cube root of x minus 2, so the first thing I'm going to do is I'm going to drop my function notation. I don't want to write f of x's in there. Excuse me. It's just going to get me really confused. So I want to swap. So I want something that I can plug y into and it's going to spit me out an x. And so for y, I plug in x. For my x, I plug in y. And now we solve. So this is the swap. And now I got to do some solving. So I want to solve this for my y quantity. So the first thing I have to do, I see y minus 2, and then I have a cube root. So the outmost thing is this cube root. How do you get rid of a cube root? Well, we cube both sides. So if we cube both sides, this side's going to become x cubed. This side is going to be a cube root of a cube. Should be y minus 2. And then the last thing we need to do to solve for this y is add the 2 over. So I have this. This is pretty much my solution right here. There's one little thing that you might want to do to fix this up, just so I know what the heck you're talking about. I'm talking about my inverse function looks like this, x to the third plus 2. Oh, shoot. And I dropped my inverse. Whoops. There should be a little inverse sign on these. So if I'm thinking about my domain of x to the third plus 2, is there anything I can't plug into a cube? No, that should be everything. If I'm thinking about the domain, or the range, I do believe it should be everything as well. Do that. 5.2. Yeah, the range should be everything as well. Nice infinity. I'm not going to be too focused on that if I'm being honest. Verify the results from part A. So if we want to verify the results, we have to come back to our definition. So f inverse of f of x, we want to verify that this is equal to x. So we want to solve this left side and verify that this is equal to x. And then we also want to do it the other way. We also want to verify that this is true. And so if I'm looking over here at the left first, I'm doing f inverse of f of x. And so I'm plugging in, I'm doing composition of functions like I was doing from the previous one. So my f function looks like the cube root of x minus 2. So we're trying to see if that's true. And then I'm plugging this to my inverse function. So I take the cube root of x minus 2. I want to take this thing, I want to cube it, and then I want to add 2. And so these two things are inversing each other. So we get x minus 2 plus 2. You might notice we're getting our x that we want out of this. So this verifies half of the definition. The other half of the definition is this thing, f inverse of x. The f inverse of x was the x cubed plus 2. Now I'm taking my x cubed plus 2, I'm plugging it in a cube root of okay. Okay, so I finished off this problem. I'm hoping you can see the work that I've done.
Where to get to? That's something.
That'll be the last time that happens, I promise. Eesh.
There's more extension cords on in the shed.
I'll have to upgrade my account, I guess.
Extension cords are on the bike in there.
And so I
Does it
finished.
just want you to update the software? 'Cause every time it drops out, it's like, hey, there's an update. Is that?
They want me to upgrade is what it is. They dropped, so the thing is they dropped the 40-minute limit and then somehow for some reason they reinstated it apparently and didn't tell me. I don't think I received any email about it. Like literally last night I was teaching a class for like almost 2-3 hours. You know, it's like there's no reason it should be doing this. It's kind of ridiculous to be honest.
It is ridiculous.
I'm sorry about this. Like genuinely, like if there was any like heads up,
No, it's not your fault, man.
like and literally like right before this class, I recorded the other lecture, the lecture that I missed last time. I re-recorded that one because I finally figured out how to use this webcam and everything. And then like now that I've started class, it wants to do this. But also the time limit doesn't come up until you have more than 2 people in your room. So that might be why it let me do that this morning. But last night, like 2 or 3 hours, I was teaching. There's not really a good excuse for why they're doing this.
Are there any of these on the test? Because this just seems like witchcraft. I don't actually.
You will have to plug. Oh man, I don't remember exactly. I have to go back and look at the quiz. There will be stuff with inverses on there. I can tell you that. I don't know if I have any verify the inverse problems. But it's very similar to the thing that we were doing previously with the composition, right? You're just looking inside. You plug in the thing, you're going from inside to outside. Same thing here. We're looking at inverse function. We're starting with our inverse. We're plugging it into the other one. Things should undo themselves, right? This is the general sort of rule. We had a cube root, and it got cubed. We had a -2. We added the 2, and it went back to my x. Similar thing over here. We have an x cubed plus 2. We're going to have to cube root it, and we're going to have to subtract 2, and we're going to get 2x. Okay.
Where did the +2 come from? The left column.
Over here?
left. Yep, there. Yes.
So F inverse is x cubed plus 2. That's coming from
Yeah,
this thing right
yeah,
here.
maybe that makes-
So my inverse function is x cubed plus 2. I don't want to plug x in there. I want to plug in that crazy thing, cube root of x minus 2. Did that answer it?
I think so. Thank you.
Yeah. Okay. What more we got? Okay, we got a few more pages, and we'll finish up like next time a little bit. But I don't think this isn't too hard to think about. Like if you know what 1-to-1 means, if we have a function, x is your radius, and this is going to give us the circumference of a circle. Why is that going to be 1-to-1? Because given a unique radius, the circumference is going to be unique, right? Those things are unique to each other. If we increase the radius, the circumference is going to increase. If we decrease the radius, the circumference will decrease. There's only one circumference you can give me per radius, right? And there's only one radius you can give me per circumference. Find a formula for f inverse of x and evaluate and interpret f inverse of 60. We'll do that next time. It's already time for y'all to switch over to your support class. I think it's getting close there.
All right, man. Well, thank you. Guess we'll
Sure.
see you Thursday morning. And then and the test is on Thursday, is that right?
Yeah, it'll open up Thursday, and I think I'm going from 9 to 9 Thursday at 9 in the morning till like 9 in the morning till Friday. So you'll have a 24-hour window to sort of open it, and then you'll have a 2-hour window to work it after you open it.
Okay. Thanks, man.
Sure.
See you Thursday. I'm gonna go to the other class.
All right, see you. On this computer. Okay. So last time, really blurry, huh? Does it like fix it at all if I like put it at a different angle? Not so much, huh?
No.
Okay. I'll read it out loud. I think you kind of see it. The function f of x equals 2 pi x gives the circumference of a circle with radius x. And they want to explain why it's 1-to-1. Oh, that's kind of silly. There's a few different ways to think about it, but like given a radius, your circumference is going to be unique and vice versa, right? If you give a circumference, that radius to that thing is unique. What I said is kind of tricky. If we think about this is f of x equals 2 pi x. We talked about like different kinds of functions. It's really kind of silly, but you can kind of think of this as like your slope. Ooh. And so if your 2 pi is like your slope, this just looks like mx. And hopefully you recognize this is just a linear function, basically. So you could think of like the circumference compared to the radius as being a sort of linear sort of relationship. And then if you think about that, if we have a line, we talked about it on the previous page, but lines pass for the horizontal line test. That's what I'm thinking. And vertical, I guess I could say, right? They pass the vertical line test and horizontal line test. And so that indicates that it's 1-to-1. So it is a function because it passes the vertical line test. It has an inverse function because it passes the horizontal. And if it passes both of these, then it is 1-to-1. Find a formula for f inverse of x. And so we talked a little bit about this, but I don't write it with the f of x symbol. Y equals 2 pi x And there's this thing you have to do. You have to swap them and solve them, or solve them and swap them. Some people do that. I think most people prefer to do the swap first. So if we're looking at this, this is a y. My y is going to become an x. This is 2 pi. My x is going to become a y. And I swap them, and now I'm solving for my, right here, my y variable. And if I want to solve for y, 2 pi times y is equal to x. And if this is multiplication, we need to divide. The thing that we need to divide by is this 2 pi. So this should look like, I'm probably just going to go ahead and flip the sides, x over 2 pi. And maybe one last little thing, I want to put this back into function notation. So my inverse function is equal to x divided by 2 pi. Okay, so that's part B. We've found our formula, and hopefully, if we think about this, if we take something, divide it by 2 pi, we're going to get this thing. This is our circumference now, and this is our radius. So we have swapped our x's and y's, right? And so now this tells us about our radius, and this tells us about our circumference. And so if we want f inverse of 60, that's the next one. Well, f inverse of 60, f inverse of x is x over 2 pi. So this looks like 60 over 2 pi. I'm going to solve this just by hand, simplify a little bit. This is going to give me what? 30 divided by pi. Do I have a number in my notes that I have? It's about 9.55, I think is what I have written. So at this point, it's got a pi in there. You're going to be grabbing a calculator. This is going to give us about 9.55. And so they say something about interpreting this. So this gives us we're talking about a circle with the circumference and radius. So probably want to think about what's the circumference, what's the radius. Well, I've kind of already said it, but this 60 is going to be our circumference. This is going to be our radius. And hopefully that's obvious because your radius is smaller than your circumference. A circle with what? Radius 60, or not radius, I said it wrong. Circumference 60 has a radius, I can't even spell radius of 9.55. And so they didn't give us units, I guess, but we can just throw the numbers in there. It'll be all right. So that's my interpretation here. Maybe wrong. So maybe one thing to take note is that we're actually swapping our x's and y's. So if this solves for circumference and this was our radius, if we do the inverse, this is our radius and this is our circumference. So those things swap around. Luis is coming in. Okay. And so this next one, I'm dropping off symbols. Let f of x equal 2x over x minus 1. And they want us to find the inverse. So I think this might be a good one to pay attention to. But same process. I don't want all the symbols in there, so I'm just going to write that as a y. I'm going to do 2x over x minus 1. And now I need to swap. And this one's a little bit different from the ones that we've done previously, you might notice, because our y becomes an x. And on this side, we have an x here that needs to become a y. And we have another x here that needs to become a y. So we're changing 2 of those variables on that one side, right? Previously, it was just like 1 and 1. Now we're doing multiple variables. So we have to solve, we're still solving for y. The thing over here that makes it hard to solve for y is that we're doing some kind of dividing thing. We don't want that fraction. So if we want to get rid of that fraction, the trick to getting rid of fractions is you always multiply by the denominator. And so if you multiply both sides by this denominator, you might notice this one simplifies. That's what we want. And we get something like y minus 1 times x. Or I could rewrite it as x times y minus 1 might be a little bit better to write. I think y'all see that a little better. Equals, and now I just have 2y on that side. Now you notice you have like y's here, you have y's here. And so if you have multiple of the same variable, if you're solving for one variable, there's this trick. What you want to do is you want to get everything with that variable to one side and everything without it to the other. And so in order to do that, I actually have to do some distribution here first. So I would do the distribution, write out all your terms, make sure it's fully expanded. Now, we want to solve for y. We have to get everything with the y to one side and everything without to the other. So there's a few ways to do that. I think the easiest way might be to what? Subtract xy. Subtracting xy would be the fastest. And so on the left side, we had a minus x left. On this side, it looks like 2y minus xy. Okay, so I said the strategy was to get everything with the variable to one side, everything without it to the other. So we've made that, we've gotten to that point. And now this is the tricky step that I think like kind of throws the most people right here. But we have it with the y here, we have it with the y here. This is not distribution, it's going the other way. So these both have a factor of y. Guess what we can do with that factor? Factor it out. And so this looks like something minus x equals y times 2 minus x. And there's like one sort of little last step we got to do to solve for y. This is y times some junk. So divide by the junk. We want to divide by the 2 minus x over here. And so minus x over 2 minus x is equal to y. And so we divided by 2 minus x in this step, right? Now, I have a minus x over a 2 minus x. If you gave me this as your solution, that would be fine. Well, actually, we should really clean it up. We should really clean it up with the function notation, right? F inverse of x equals a minus x over 2 minus x. You should really clean it up to at least like something like that. This is probably not what the book is going to do. They're probably not going to lead with the negative on top. And so they're going to get rid of a negative. If you see this in the book, it will probably look something a little different. And I don't know if you've multiplied these things, but if we do a 2 minus x, right, and we multiply 2 minus x by a minus 1, the 2 becomes negative and the x becomes positive. And so what essentially kind of happens is you're swapping them, right? Because if you think about numbers, like 5 minus 2 is going to give you 3, but if we do 2 minus 5, it's going to give you the negative of it. And so those two things relate by a factor of a negative. So if you swap the order you subtract things in, they relate by a factor of a negative, right? So 2 minus x, and if we multiply it by negative, it will be x minus 2. So in the book, it will probably say something like that. They're probably not going to have a negative on top. Questions on this? Okay, what does it say? Example 7. Oh, I don't want to do this. Is a domain restriction. They said not to do these. I meant to cut this out. We don't need that. Domain range. Yeah, I don't want to do all this. That's not going to help you out. Domain of f. And so I think this shouldn't be too difficult. They said to lighten up a little bit on those domain things. It's a parabola. So if we think about this, it breaks the horizontal line test because it's going to hit it in 2 points. So there's a thing that you can do called restricting the domain. If we want to create this as a function and an inverse function, we can restrict the domain, and we can literally just like take away half the graph and only talk about half a graph. And so we talk about half a graph, we can have a function and we can have an inverse function basically. And so that's the gist of this problem in like 3 seconds. There you go. And so if we want to think about the domain of f, and I'm hoping this is sort of the picture you have in your mind. We have a set of x's, we have a set of y's. And f is this sort of function that takes an x, and it goes from x to y. And the inverse is going to take the same, and it's going to inverse it. It's going to take it that way. And so if we think about this is our domain, this is our range. So if we think about the original, our domain of x, our domain of f, is going to be the same thing as our range of f minus, right? Does this make sense, hopefully? And this would be our domain for our f minus. So our domain of f is going to take it, be the x's in our f function, but they're going to be like our y's in our inverse function. So this is going to give us the range of the other one, and the domain of this one is going to give us the range of the other one. And so this looks probably really confusing, but the easiest way to think about it is you swap your domain and range, basically. The domain of one is the range of the other, and then vice versa, right? Okay. So this is a quick like graphing inverses. So we want to think about like how inverses in their graphs look. So if A comma B is in F, well, F takes A to B, then F inverse would take B to A. And so if we want to think about how these points are going to relate to each other, if you look at the diagonal, these are going to be both equidistant from the diagonal. And we can kind of justify that with the square coordinates and everything that's there. We can do a sort of geometric proof proving it. I don't want to spend a lot of time on that. If you graph enough of them, I think you're going to kind of see it, and it will probably be a little bit better to just kind of look at it and determine that way, I think. So graph F and graph F inverse and y equals x. So this line is the y equals x line. If this is our f function, we want to take some points on here. So let's grab some points. Here's a point. Here's a point. Here's a point. So this is -1, 3. This is 0, -1. This is 2, 3. And if these are all on my f function, can you guess what the points on my inverse will be? That's the next thing, right? Well, if f takes 2 to 3, f inverse is going to take 3 to 2. So I'm trying to think of a way to say this without it sounding silly. But basically, we take this and we flip them, right? You flip your x and your y, and that gives you your inverse. And so we know these points. We just got to graph these points. What is it? 3, -1 should be right here. Yeah, I should do this with a different color, huh? 3 -1. I got -1, 0. And 3, 2. Why not? Did I do something wrong? 2, 3. I've got 0, -1. I have -1, 3. I have 3, 2. -1, 0, and oh shoot, this should be -3. That's what I did. -1, -3. Whew. That'll get you. So -3, -1 right here. So this point should not be a point. Sorry about that. So this is what our line should look like. And if we look, we should be able to see this is my y equals x. If I go like diagonally through that line, it's going to be equidistance, right? We see this sort of reflection sort of thing happening. It's going to be each of these points is equidistance across that y equals x line. So it's a sort of reflection across the y equals x line that's going to happen to these things. And so I wouldn't really, I mean, it's a good way to think about it and know it, that it is going to be the reflection. But if you want to graph it, like this is the way to graph it. Make sure you get your points. Make sure you put in all those negatives. Those are pretty important. And just flip them, right? Flip your x and your y, and it will give you your new graph. Pick some points and flip them. Questions about that? Last thing on this thing. So f of 2. So this, I think we've had similar things like this, but we're just picking, we're using our graph to pick values off of. So if we do f of 2, I want to go, this is my x value in my f function. So I want to go where my x is 2, and I want to see what my correlating y is going to be. And so that says -3. That is if we're doing f, and so they're trying to set you up, prime you for this next example. So if that's our f, and we plug in an x, what quantity are we going to plug into our inverse? That's right. Shh, chill. There's another dog walking by, apparently. And so if our f takes x to y, this is going to take y to x. And so this quantity, it's not an x quantity, hint, hint. It's going to be a y quantity. So now we want to look at the y's, and we want to see the correlating x that happens. And I've kind of set you up for this one, because if we plug in a -3 to this, we're going to get the x value of 2. Are the dogs like loud in this thing? They're pretty loud in my apartment. Sorry about that. They get excited about another dog walking. Okay. So if the y is a -3, my x is going to be 2. Same thing here. We want to look here. This is a y value. So if my y is equal to 1, so I'm coming along here everywhere where my y is equal to 1, and I'm looking, my y is going to be equal to 1 right here. And when my y is equal to 1, my x is equal to 0. Any questions about this? I think this is the last page on here. Yeah. So that's 5.2. That should be the last thing that you need for your test. I think I might stop the recording and then just like continue working from the quiz if y'all want, if that sounds fair.
Yeah, that sounds good.